Welcome to AP Chemistry. This unit focuses on the formation and analysis of buffer systems with its related equilibria. We begin with a common wet chemistry technique called titrametric analysis. Here, a titrant with a known and standardized concentration is used to analyze the unknown concentration of an analyte. In this case, the analyte is hydrochloric acid, placed here within an Erlenmeyer flask. A pH probe is also inserted into the flask to measure the pH as the titration progresses. Before the titration has begun, the pH of the analyte is only dependent upon what was initially placed into the solution, in this case, the hydrochloric acid. Some deionized water was also added to the flask to help with adequate stirring. This is why the calculation provided will be somewhat lower than the pH measured. Now that the titration has begun, we must do a stoichiometric calculation to find what will remain in the solution to affect the pH. Since hydrochloric acid is still in excess, the pH is still very acidic. Again, we perform a similar calculation here. And here as well. However, in this case, we now approach the equivalence point, a point at which the reactants are in exact stoichiometric relation to each other. At this point, the pH of the analyte will only be dependent upon water, and the pH will be 7. Beyond the equivalence point, we will have over-titrated the analyte with our titrant, and the pH of the sample will now be dependent upon the amount of sodium hydroxide that we will have added in excess to the solution. And finally, one further calculation is performed similarly to the previous as well. This thus yields us a complete titration curve. If analyzed properly, we can find the exact point, experimentally, at which the reagents have completely reacted with one another. If the concentration and volume of the titrant is known, and the volume of the analyte is also known, we can find the exact original concentration of the analyte. This specific titration is called a strong acid, strong base titration. Typically, sodium hydroxide is standardized by weighing precise amounts of sodium hydroxide and placing it into a precisely measured solution. This standardized sodium hydroxide can then be used to standardize hydrochloric acid solutions by the method which we have just shown. Nevertheless, neither strong acids nor strong bases ever play a role within an actual buffer system. A buffer system is by definition a system which has both a weak acid and its weak conjugate base, or a weak base and its weak conjugate acid within the same system. The reason for beginning this video with a strong acid, strong base titration is due to the fact that the most common method used to make buffer systems will be with using either a weak acid and titrating with a strong base, or beginning with a weak base and titrating with a strong acid in order to create the buffer system that we will now analyze. The most effective buffer system is one in which both weak species, either weak acid and its conjugate weak base, or a weak base and its conjugate weak acid, are close to equal amounts. The Henderson-Hasselbalch equation, provided at the bottom, will be commonly used to create a buffer system, using Ka values from different possible systems, in addition to a prescribed pH that is desired. The point of a buffer system, as you probably already have encountered, is to resist any changes in pH. This works according to the following. If a strong acid were to be added to a buffer system, it would react with the weak base of the buffer system to produce more of the conjugate weak acid. This weak acid would be much weaker than the original strong acid that was initially added, and the pH would change only slightly. Conversely, if a strong base were to be added to a buffer system, it would react with the weak acid of the buffer system to produce more of the conjugate weak base. This weak base would be much weaker than the original strong base that was initially added, and the pH again would change only slightly. This is how a buffer system resists changes in pH. The strength of a buffer system is dependent both upon their concentrations and their concentrations relative to each other. It is most preferred that their concentrations be very close to equivalent with each other. For example, if a pH of 4.30 was required for a certain buffer system, we should choose the benzoic acid benzoate ion buffer system since its pKa value is closest to the required pH. This is because the ideal ratio of weak acid to weak conjugate base is 1, and the log of 1 is 0. Therefore, the best buffer systems will be one in which the pKa of our system matches the required pH. Now, it is common that to prepare a buffer system will require a bit of titration. Titrations can also be performed to find the original concentration of the analyte in question. Every weak acid must be titrated with a strong base, and every weak base must be titrated with a strong acid. Here, at the beginning of the titration of acetic acid is the only species present, along with water, that will affect the pH. A simple equilibrium calculation allows us to find the pH here. This time, the calculations will be very similar to the actually measured values. Now that the titration has begun, a stoichiometric calculation is first required. The resulting species are the acetic acid and acetate ion. This qualifies as a buffer system, and instead of creating another ice table, we can simplify the process by using our buffer equation directly. Remember, this buffer equation was derived from the equilibrium expression. This means that an ice table would yield exactly the same calculation as using our buffer equation. The buffer equation just makes the process of finding the resultant pH significantly quicker. Here again, the process to calculate the pH is very similar. And here again as well. Note that at this point we have just passed the point of our most ideal buffer system, when the pH is equal to the pKa value. We call this the midpoint on our titration curve. And here the calculation is similar as well. We now approach the equivalence point of our titration, but this equivalence point is extremely different from the one in which a strong acid was titrated with a strong base. There, at the equivalence point, the only species that affected the pH was water, and the pH was exactly 7.00. Here, however, the major species is the acetate ion, the conjugate weak base, and water. The pH calculation thus requires that we find the resulting concentration of the acetate ion and then to use an ice table calculation to find the pH. Remember that the Kb for acetate ion must also be here used as well. After this point, however, the pH is dependent upon the excess of sodium hydroxide that has been added, and the calculation is radically easier. Note how the entire titration significantly differs from the strong acid, strong base titration curve. Weak acid or weak base titrations will always look more like an elongated S. Finally, for titrations that are performed routinely, we may use a pH indicator, which can indicate the equivalence point of the titration by changing color. Since the equivalence point is technically different from the point at which the indicator changes color, we give the point at which the indicator changes color another name. That is, the end point of our titration. Now, all an indicator is simply another buffer system. It is important to note that the indicator does not need to change color at exactly the equivalence point of the titration, only within a certain allowable range of the equivalence point of the titration. This is plus or minus 1 of the equivalence point pH in the titration curve. In this sense, the endpoint of a titration is really the midpoint of an indicator, and it is most ideal for this, the midpoint, to match the equivalence point of our titration. What this means practically for us in selection of an indicator is to use one in which the pKa value is closest to the equivalence point pH in our titration curve. Note how in a strong acid, strong base titration, either phenolphthalein or methyl red could indicate the equivalence point, but only phenolphthalein could be used for the weak acid titration provided to the right. We will also take class time to work with titrations of polyprotic acids. Some will have clearly delineated curves, like maleic acid below, because the Ka values differ significantly. However, others like sulfuric acid will have two acidic protons that will be so close as to be difficult to distinguish on their titration curves. Here, two triprotic acids are shown in comparison below. Till next time we consider the mysteries of the absolute, crib.